So my name is Mohammed Display. As Stav mentioned, I'm a master's student in statistics here at KAUST. I'm originally from Riyadh. Last year, I graduated from MIT with a degree in chemical engineering. And some of you may wonder, what's a chemical engineer doing in statistics? It seems kind of weird. I thought the same until I actually started. And over the past year, I've come to realize that statistics can add a lot of power and insight to any field that deals with data. And that's precisely what we're here to explore today, the power of statistics, extreme or environmentally friendly. So today we're joined by 6 esteemed panelists, 4 of whom are professors in the statistics program here. One is a PhD student and one is a postdoctoral researcher. We'll introduce them one by one and then hopefully have time for an open Q&A session. So first up is Professor Raphael Huser, who does work on statistics for extreme events.
Thank you, Mohammed. Extreme events are everywhere. They affect us as a society, they affect the economy, and they affect the environment. But what are exactly extreme events? How can we define them? How can we analyze them statistically? Is it possible to predict them? And why is it so difficult to make such predictions? An extreme event, by definition, is something that occurs with very low probability in statistical terms. In other words, it does not occur frequently, but when it does, and it will, it might have dramatic consequences. And that's why we should care about the modeling of extreme events. So to give you a concrete example, I put here on this slide behind me a few pictures, and you can have a look at the bottom right picture. So this is an article taken from a local newspaper, and it talks about a flood that hit the city of Jeddah in November 2015. And you can see that several streets were completely flooded, so it was a pretty extreme event for the city of Jeddah. On the left, you can see an animation with maps, which basically shows you the annual maximum rainfall amount that basically fell on the Arabic Peninsula from 1998 to 2014. So the question that we may ask from this is, well, based on the data on the left, what was the probability that an event on the right happens? How likely was it that such a big extreme event could occur? Was it likely or was it unlikely? So this is statistics of extremes. This is the type of questions that we ask. So why is it so difficult now to predict extreme events? Well, to explain this, let me shift to another example, which I think illustrates very well the question and the problems. This is related to the North Sea flood of 1953. So let me tell you this story. On the night of January 31st to February the 1st, 1953, a combination of a high spring tide and a severe European windstorm caused a storm tide in the North Sea. So the water level locally exceeded 5.66 meters above mean sea level. The waves and the floods and the water overwhelmed the sea defenses and caused extensive flooding in the Netherlands and neighboring countries. And as a result, more than 2,000 people died from this flood. So the Dutch government set up the so-called Delta Commission, which conceived and deployed an ambitious flood defense system, which was called the Delta Works. And it has now been declared one of the 7 wonders of the modern world, according to the American Society of Civil Engineers. So imagine for a second that you're a civil engineer. You're part of this Delta Commission in 1953, and you're asked to build a system of dams and dikes to protect the estuaries of 3 rivers, the Rhine, the Meuse, and the Scheldt, and protect different cities of the Netherlands, including Rotterdam. Of course, you have to face a compromise. You don't want to build the dam too low, otherwise it will be unsafe for the nearby population. But also, you don't want to build it too high, because it's too expensive, and you have a limited amount of money. So if you spend too much money on one particular dike, you have less money to spend on the other dikes, and it becomes unsafe for another region and another part of the population. So you have to face this compromise. So the Delta Commission, what they decided to do is to set the acceptable risk according to region. So for example, in North Holland, they decided to set the acceptable risk in such a way that the flood defenses would resist against a future storm event, big extreme event, that would occur only once every 10,000 years. Of course, such risk assessment has to be based on data, but collected on a much shorter time period. So this illustrates two main challenges related to the modeling of extremes. The first one is that we don't have a lot of data. There is a lack of extreme events in the data set that we have, because by definition, extremes are scarce. And the second challenge is that it is often required to make extrapolations to future extreme events that exceed any previous measurements, that reach levels that have never been observed in the past. So that's why statistics of extremes, which is based on a very elegant, mathematically rigorous framework, which is called extreme value theory, can be useful. It provides models and statistical methods that can make such extrapolation in a rigorous manner.
Thank you, Professor Huser. So you mentioned this very elegant and rigorous framework, and we've seen how it can be used in this application. Are there other domains that this framework might be applied to?
Yes, so I mentioned heavy rainfall in my example here, but this theory is very general and could be applied to many different kinds of data. So it could be also extremely low rainfall, which is obviously linked to droughts. It could be extreme temperatures like heat waves, or cold temperatures, cold waves, or extreme wind speeds. It could also be applied in other fields that have nothing to do with the environment, like financial extremes, big losses in stock markets, or financial crisis. So the theory is very general, but it has many, many applications.
Very cool, thank you. So our next panelist is Sabrina Vittori, who's a PhD student here in the statistics program, and she does research on air pollution indices.
Thanks, Mohammed, for the introduction, and good afternoon to everyone. During my studies here at KAUST, I focused on air pollution extremes application. Air pollution can be caused by both human and natural actions. For example, vehicle emissions or the waste we throw in the landfills or agriculture are among the main anthropogenic causes of air pollution. Whereas natural forms of air pollution are, for example, wildfires or dust storms or volcanic activities. So why are we so interested in studying air pollution extremes? Well, because in fact, the exposure to extreme concentration of air pollutants can cause serious negative health effects on humans and environmental problems such as global warming, climate change, and limit crop productivity and degrade ecosystems. My main challenge here at KAUST was really to understand how to estimate the probability of different pollutants to be extreme at the same time. And to do so, I developed a new statistical methodology based on extreme value theory to be able to model the behavior of different air pollutants, extreme concentrations simultaneously, and also to understand how these relate to extreme weather conditions. The Air Quality Index is a measure used by the US Environmental Protection Agency to communicate air quality standard to the public. And during my study, I also looked into air quality indices for some criteria pollutants collected in California, where the air pollution monitoring station network is well established. And I found that their air pollution policies did succeed in decreasing air pollution. However, further efforts are necessary to protect public health, reducing emissions, and also to protect the environment in this area. Thank you.
Great. So I know that I would not like to inhale any of the chemicals in this list, but can you explain what we're seeing in the left plot here?
So the air quality index is divided into different categories, which represent different level of health concern, and are indicated by different colors in this graph. So the yellow means acceptable air quality, the orange means unhealthy air quality for sensitive group of people, and the red unhealthy for everyone. So basically, looking at the graph, you can conclude that the average air quality index is expected to exceed the acceptable threshold, so the yellow box, at least once a year in the next 2 decades, and is expected to exceed the unhealthy threshold for sensitive group of people at least once every 10 years on average and under stationary conditions.
All right, that's a little worrisome.
Yeah, I know.
Our next panelist is Professor Mark Jensen, who does research on big data for environmental statistics.
Thank you. Thank you, Mohamed. Hello, everyone. So if you recall the title of this Café, it's about the power of statistics, extremes or environmentally friendly. So you've heard already a bit about extremes, and now I'm going to shift the focus on environmental problems. So my group is interested in environmental problem. In particular, one example is to study the climate. So how do we study the climate? One possibility is to define a model to look at how the climate will evolve through time. So a climate model is basically a very complex system of equations that describes the physics of oceans and the atmosphere and how they are coupled. And such a model is run on a supercomputer. It's so complex. A supercomputer, for example, like the one we have at KAUST. The problem is that it takes a lot of time to run a very complex model. So if we start one right now, it's not going to be over in a few minutes. It's going to take weeks or months. So for example, it could take, let's say, 6 months to get an output of the climate model. So what we're trying to do here is to use statistics to fit a fairly simple but realistic spatial temporal statistical model to the output of the climate model. So this is called an emulator, and we can fit such a model fairly quickly, and we can simulate from it very quickly, so that we can have many realization. We don't need to run the climate model again, but we can generate many realization of the climate model quickly. So what you see on the screen on the upper right figure, the two spheres rotating, is the output of the climate model, one of them is indicated, and the other is basically the emulator that is trying to reproduce that output. What we're looking at there is temperature on Earth for years from 1850 to 2100. So we have a certain scenario on how the CO2 will evolve in the future, and this is an input in the climate model. And so the data set of temperature is actually 3-dimensional on Earth. So if you represent Earth as a sphere, you will have different layers. In fact, we have different altitude, 17 levels of altitude, and this is going to generate a data set of 1.4 billion observation. So this is very big. This is what we call big data, big environmental data. So what you see in that movie, you see the years going by from 1850 to 2100. The small graph describes the CO2 as it's evolving through the years, and essentially what is the color scheme that is represented on those spheres are differences of temperature with respect to 1850 and the current year as described. So if we want to visualize this data and show it to the public, we have developed also an app for that. This app is called Statistical Emulator, and you can download it. If you have an iPhone with you, you can download it right now and look at it. And what you will see on this app, and this is described in the bottom left of the screen, is basically, again, those two spheres representing temperature on Earth. You see that you can stretch them and magnify the different region. You have 3 buttons, essentially white buttons, and the first one allows you to rotate the sphere. Currently, it's centered on Africa and Saudi Arabia, but you can look at different parts of the world. You have another button with which you can change the altitude, so you can look at the temperature at different altitude. And the third one is a button that allows you to change the speed of the years going by in the experiment. Now, since today we have a very special audience here, we have also a secret button, so I will tell you what this is. So if you look at the little button on the left upper corner, the square button, this is the virtual reality button. So if you click on that, you're going to go in virtual reality. If you have Google Glasses, you can use your iPhone to look at the output in 3 dimensions. So it's actually quite cool, so have fun with that. Thank you.
Thank you, Professor Genton. So if we're looking at this globe, clearly your research has global impact. I'm curious how this methodology can be applied to something specific to Saudi Arabia. Do you have any examples of this?
Absolutely, Mohammed. So this is a great question. In fact, I have currently a follow-up project that is looking at emulation of wind fields. So it's a similar problem, but if you're looking at wind, it's a quantity that is much more difficult to handle because it's not just one number, but you have a direction also of wind. And wind is very relevant, in particular, I think, to Saudi Arabia for reason of renewable energies. And as you know, winds do not stop at the Saudi border, so they come from other regions as well, so you have to think about them globally. And so one application of that project is to think about future renewable energy potential in Saudi Arabia. Great,
thank you. So our next panelist is Professor Ying Sun, who does work on statistics for complex data visualization. Where'd it go? Take it away.
Yeah, I think. Thanks. Hello, everybody. So it's a great pleasure to be here to discuss the power of statistics. In KAUST, my group works on environmental statistics. You already heard from my colleagues, statistics is a subject of learning from data. And we know in environmental applications, data sets are often large and complex. Traditional statistical method face a lot of challenges. As statisticians, we need to develop new methods to deal with complex data set. So today I'm going to talk about statistics for complex data visualization. When I talk about data sets, you may think of a string of numbers. As listed on the, in the first example, I have 11 numbers there, 1 to 9, and 21, 22. So the number 6, as you can see, is in the middle position. So we call this the median. And 21, 22, we call these two values extreme values or outliers because they are far from the rest of the data. In statistics, the classical box plot displays such information nicely. For example, the number 6 is displayed as the black line in the middle of the box. And the two values, 21 and 22, are marked as outliers in the classical box plot. Now think about if our data set becomes more complicated. For example, if I have a set of curves, as in the second example, there are 58 curves representing sea surface temperatures from January to December. By only looking at those curves, it is very difficult to say which one is the most representative one or the median curve. So in my group, we developed a new visualization tool called functional box plot as a strong analog to the classical box plot. As you can see in the functional box plot, the black curve in the middle shows the functional median. That is the most representative sea surface temperature among samples. And also the functional box plot detects two outliers. Those two curves correspond to extreme events. Similar ideas can be applied to a set of images or surfaces. For example, if I apply the functional box plot to a set of fMRI brain images, we can identify median and outliers. So in this application, the median means the most representative or the most normal brain scan image. And those outliers may suggest those images are abnormal results. The functional box plot has many applications. For example, it can be used for brain signal visualization. In the picture, it is my collaborator who volunteered to have his brain activities recorded. So we use functional box plot to visualize the brain activities from different regions. If you didn't use functional box plot before, hopefully in the future you have the chance to try it out. It's very useful. Thank you very much.
Thanks, Professor Sun. So a lot of us are familiar with traditional box plots, but can you explain some of the challenges in going from traditional to functional box plots?
Yeah, that's a very good question, because in the classical box plot, you see the first step is to sort all these numbers. The data set I gave here already sorted. So in the functional box plot, similarly, the first step is to sort all these curves. So you can imagine this is not trivial because there's no natural ordering over there. So that's our contribution. We propose a way to sort all these curves, then construct such a box plot to visualize curves. Yeah,
Great, thank you. So our next panelist is Dr. Carolina Ewan, who does research on statistics for brain activity.
Thank you. Hello, everybody. So today I want to talk a little bit about one of the main motivations of my research here in KAUST, which is the study of brain signals. We believe that the neurons need to act together in connectivity to realize a specific task, such as learning or a motor task. And this connectivity has been captured the interest of many research. We need to understand how the brains react to develop this task. In particular, we also are interested in studying the connectivity and how this connectivity can be affected by a specific disease. Here I have an example of EEG recordings on the left side of the slide, where you can see the EEG traces of a patient who suffers an epileptic seizure. And here, the main interest is to understand if this connectivity has been affected by the seizure. We apply statistical models that belongs to clustering methods area to describe this connectivity between different brain regions, and also to quantify the probability of this connectivity. In the right side, you can see in the bottom part, there is an animation that shows the different connectivity of the brain regions during different time points. And in the top part, you can see between these two different scenarios, before seizure and after seizure, how these probabilities change. So with this methodology, we can conclude that this epileptic seizure has an effect on the connectivity of the brain. So this is one of the examples what we can do by using statistical models in this area.
Thank you, Carolina. So I think this is a beautiful example of what we mentioned earlier about statistics, bringing a lot of insight to any data-driven domain. Is there any unique challenge to working with brain data?
Yeah, one of the main challenges in this part is that we cannot observe the brain signals itself. We believe that the EEG channels capture the brain signals, but that produces also that the signals captured are very noisy. So we need to quantify the uncertainty behind the signals that we observe. That's why the probability has a central role in this study. Another challenge is that to make more accurate conclusions, we need to establish a multidisciplinary work between people, in this case, from neuroscience, and in some other statistical applications also.
Great, thank you. Our final panelist is Professor Haavard Rue, who does research on Bayesian statistics, and he's recently been very involved with a tool called R-INLA that is very popular in the field.
Hello, and yes, I'm going to talk about a little bit more generic kind of research that are not kind of particularly focused towards any particular application. So the curious thing on what we kind of really work on are kind of models or results from statistical models that are close to Gaussians. I guess most of you have kind of heard about the normal distribution or the Gaussian distributions. And it turned out that the results from many statistical models are close to Gaussian distributions. And this kind of observation is what enabled us to kind of compute very quick and very accurate approximate solutions to very hard statistical problems. And this is what my group is working on. And we also kind of distribute our results in statistical software so the world can use it. And on this slide on the left, I show some results of models that have been analyzed with our software. And this is from the World Health Organization. So this is the director from the World Health Organization commenting on a big study of the effect of malaria or how to fight malaria in Africa during the last 15 years. And this is a snapshot from the BBC News. And this kind of study used kind of extensively our models and also statistical software and everything we do to do the analysis. On the right, there is more recent work, again from the World Health Organization, studying the effect of the pollution on health. Okay, and also this is kind of a worldwide study involving all the data from all the major cities in the world, and extensive health data as well, and merging all these to do an overall huge kind of statistical analysis. And this is kind of putting numbers on things how bad pollution is for our health.
Thank you. So I'm curious, what were people doing before R-INLA, and how did they start doing it after the software is available?
So for many of the models, so like the models that we see here, by now there is no kind of good alternative way to do it. You know, the models are simply too large, and there are no other software can really do this by now.
Great, thank you. So before we move on to the Q&A, just like to encourage you, if you'd like to learn more about the research that the program does or about our faculty members, please visit stat.kaust.edu.sa. And now we can welcome questions بالعربي أو بالإنجليزي. كل واحد.